We're going to be looking at quantifiers and predicates. So here's an example of a question. Did you know that all mammals have hair? Maybe you knew that or not. Did you know that every integer is even or odd? Did you know that some odd numbers are not prime? So our goal is to write statements such as these using mathematical notation. And these are sort of questions, but we could turn them into statements. And um, I guess they're questions because of the did you know part. But yeah, we can think of these as statements and we want to write these out using mathematical notation. The kind of key thing here is that we've got words like all and every and some. So we want to be able to kind of convert words like that into mathematical notation. This helps us clearly understand the logical structure of mathematical statements. So a predicate is similar to a statement, but it contains what's called a free variable. So an example would be P of x is the statement that x is prime. So you can see that x in there is a free variable. So we sort of have this statement P, but it's predicated on the variable x. So the predicate itself is not a statement because its truth value depends on x. Once we substitute a value in for x, it creates a statement. So some examples would be P of 7 would be the statement 7 is prime. That is true. Another statement could be P of 8. 8 is prime. That one is false. Predicates can be turned into statements using quantifiers. So we have two quantifiers. The universal quantifier, this sort of upside down A, is read for all. And then the existential quantifier, this sort of backwards looking E, we say there exists or for some. So we could have, again, the P of x is prime. We could include a quantifier here, which says, for all x, P of x, so every number is prime. Now that is a statement. We don't have to plug a number in for x. We have a statement. It happens to be a false statement because not every number is prime, but it is a statement. Another example would be something like this. There exists an x such that P of x. So there exists a prime number. This one is true. Of course, we know that there exist some prime numbers. So you can see how we can turn a predicate into a statement without having to plug a number in or plug something into it by including a quantifier. Some more examples, we could have the predicate E of x is the predicate x is even. So this first one would say for all x e of x, that says basically that every number is even. That is a statement, it is false. This one says there exists an x such that e of x. So there exists an even number. This one is true. There does exist an even number. This says for all x not e of x. So that means that every number is not even, or said a little bit more succinctly, we could say every number is odd. Being not even is the same thing as being odd. So every number is odd. That is a statement. It is false. Or there exists an x such that not e of x. So there exists an odd number. This again is a statement, and it is a true statement. There does exist an odd number. We can also look at some more universal statements. So a common form we might see for a statement is every blank is blank. And so we can write this out using a universal quantifier for all x. If P of x, then Q of x. So kind of the blank blank, the P of x would be this first blank, and the Q of x would be this second blank. So for all x, if P of x, then Q of x, every P of x is Q of x. For all x, if P of x, then Q of x. So an example, all mammals have hair. If M of x is a mammal, H of x is x has hair, we could write for all x, if M of x, then H of x. If x is a mammal, then x has hair. Another common form we might see is statements of the form some blanks are blank. And so we can use an existential quantifier here. and write there exists an x such that p of x and q of x. So here we might put p of x here and q of x here. So some blank are blank. There exists an x that is both p of x and q of x. So some whatevers are kind of these two things. So some cats can swim. If c of x is a cat, s of x is x can swim. There exists an x such that c of x and s of x. There exists an x such that x is a cat and x can swim. So some cats can swim. There exists a cat that can swim. So let's try this example. Every student likes mathematics. So here we have kind of two predicates, x being a student. Maybe we'll write that as s of x, and m being likes mathematics. So we could say for all x, if s of x, so if we've got a student, then m of x, then that x likes mathematics. So for all x, s of x, if s of x, then m of x, every student likes mathematics. And then some dogs are brown. We could have d of x being that x is a dog, and b of x being that x is brown. So we could write there exists an x such that d of x and b of x. There exists an x such that x is a dog and x is brown. Some dogs are brown.